We want DNA to be digital. I've been doing this for 13 years now. I've been working on trying to get DNA nanoelectronics to work. This is the first device. It's a step towards circuits. The paper that we published in Matter, we call it the transistor paper because it's the first DNA switch. We used a DNA base pair which binds to metal ions. So at neutral pH, we used TT, those are DNA letters. It'll bind a mercury atom and a mercury atom, so it binds two mercury atoms. If I raise the pH a little bit, one of those mercury atoms flips to being a silver atom. And if I keep raising the pH, I get two silver atoms in the same spot. So the DNA has not changed, but I've switched out the metal ions that exist in the double helix. So we cut, I mean we don't really cut, but we essentially cut the sequence out of the crystal that we know the chemical reaction on, and we put it down on a microchip, and we hooked it up to molecular leads, and we just replicated that chemistry. When you change the pH, the metals move, and when they move, current flows at a different rate because silver is more conductive than mercury, and that is a pH switch. That is writing electrical information into the double helix, and then we read it because we have it hooked up to a chip. We built the first DNA transistor, the first of many, and we're going to make lots of devices, and now that we know what we're doing, we can be smarter about it. I think the people in this lab are very interested in atomic precision. If you know where every atom in your structure is, no matter how big the structure is, then you can move them around and get information out. And I think that this focus on really big structures with really tiny single atom components gave us the ability to make a single atom transistor.